Imagine for a second that you are staring at a completely blank, perfectly smooth white canvas.
Right, just a totally empty surface.
Exactly. It looks incredibly simple, just empty space waiting for something to be painted on it.
Mm.
And
So,
we usually think of the universe like that, too.
yeah, we tend to view empty space as just, well, empty.
Right. A passive, quiet stage where stars, planets, and galaxies just happen to do their thing. But what if you took a microscope to that blank canvas and realized it wasn't smooth at all?
What if it was actually a hyperdense, vibrating, insanely complex machine?
Exactly, made of these tightly packed gears, actively working every single microsecond to keep reality from just falling apart. Welcome to today's deep dive. We are taking you on a journey into one of the most mind-bending, independent research papers in modern
It
physics.
really is a massive paradigm shift.
It's called Infinite Fractal Descent, written by Encomgallen and Nazandajargal. And our mission today is to completely tear down how you think about empty space, what actually happens inside a black hole, and honestly, the very fabric of reality itself.
It's a profoundly radical paper. But to appreciate why a framework this massive is even being proposed, you have to understand the ultimate boss battle that has been raging in physics for decades.
Oh, the irreconcilable war.
Right. We have been stuck between our two best, most successful descriptions of reality, general relativity, and quantum mechanics.
The two heavyweights that absolutely refuse to be in the same room together.
Okay, so
You've got general relativity handling the massive stuff. Gravity, the orbits of planets, the bending of starlight.
and then you have quantum mechanics handling the microscopic stuff, atoms, subatomic particles, the weird probabilistic nature of the tiny.
And they both work flawlessly in their own domains, but when you try to combine them, the math literally explodes.
It really does. And the breakdown happens most dramatically when you look at extreme gravitational conditions, specifically inside black holes.
Right, the ultimate stress test.
Exactly. General relativity follows its own logic all the way down to a catastrophic conclusion. It predicts that matter crushes inward infinitely into a singularity.
A point of literal infinite density.
Right. But infinity isn't a number you can actually measure. In physics, infinity is usually a sign that your theory has reached its breaking point.
It's a red flag.
Exactly.
Mm-hmm.
And quantum mechanics looks at that singularity and objects entirely. It dictates that you cannot have infinite density. And more importantly, you can never, ever destroy the quantum information of that matter.
Which brings up the information paradox because black holes threaten to do exactly that.
Yep.
We know from Stephen Hawking that black holes aren't totally black, right? They leak energy over trillions of years, Hawking radiation, and eventually evaporate entirely.
But standard physics suggests that this radiation is random.
Meaning the original blueprint or the information of whatever fell into the black hole is permanently erased, which quantum mechanics says is strictly forbidden.
Right. And add to that the problem of empty space itself. It's known as the vacuum catastrophe.
Oh, this one is wild.
It really is.
Yeah.
When quantum physicists calculate how much background energy should be vibrating in the totally empty vacuum of space, the number they get is 120 orders of magnitude larger than what cosmologists actually observe when they look at the universe.
120 orders of magnitude.
Yeah, it is famously one of the worst mathematical predictions in the history of science. So we're dealing with infinite singularities, evaporating quantum information, and a vacuum energy that makes zero sense.
It's a mess.
It is. But the Infinite Fractal Descent Framework, or IFD, attempts to resolve all of those breakdowns with one fundamental, sweeping paradigm shift.
Okay, let's get into that shift. Because the IFD framework argues that the only way to fix these breaking points is to stop looking at the canvas of the universe as a continuous empty sheet.
Right, we have to fundamentally overhaul our view of the vacuum itself. That is the core ontological shift of the paper. We must abandon the classical idea of a continuous spacetime.
Like a smooth continuum you can divide infinitely.
Exactly. Instead, IFD proposes an IFD discrete matrix. This requires a conceptual leap. What we perceive as empty space is actually a structurally complete, immensely high-density matrix of discrete individual units.
So the vacuum is not a void. Space is already completely full.
Exactly.
I always try to visualize this like zooming in on a digital photograph. From a distance, a photo of a clear blue sky looks completely smooth and unbroken.
But if you zoom in far enough...
Right, you realize that smoothness is an illusion created by your distance from the object. The sky is actually made of incredibly dense, perfectly packed individual pixels constantly updating with digital code.
That's a great analogy.
But in the IFD framework, what are these pixels of the universe actually made of?
Well, the framework describes them as densely packed spheres, existing at a nested, infinitely smaller fractal scale.
Okay.
The paper designates our everyday macroscopic world like the scale of planets, humans, and atoms as S sub n.
Got it. The normal stuff.
Right. But the subscale, the incredibly dense microscopic matrix that actually forms the vacuum of space beneath our notice, is designated as S sub n minus 1.
S sub n minus 1.
Yeah. And this builds on a concept called the dodecahedron linear string field hypothesis. Space is essentially a dynamic, self-correcting code anchored by what the paper calls a dodecahedral core.
A geometric 12-sided structural anchor.
Precisely.
Okay, so we have this ocean of S sub n minus 1 spheres completely packing the universe. My immediate thought is about the sheer logistics of moving through something that is already completely full.
Right, the friction of it.
Exactly. If the vacuum is essentially a solid block of tightly packed fractal spheres, how does anything move? Like, how does the universe handle chaos or shifting energy without physically grinding to a halt or just breaking under its own dense complexity?
Well, the universe doesn't freeze up because it has built-in mechanical failsafes to prevent structural collapse. According to the IFD framework, the vacuum matrix isn't rigid or static. It goes through phase transitions. Mostly, it exists in a neat, orderly periodic phase called the tame phase.
The tame phase. Nice and quiet.
Exactly. But when subjected to stress, or, complex energy interactions, it can transition into a chaotic wild phase, specifically something called an elongated phase.
Elongated. That makes me think of something being stretched out like a rubber band. Are you saying this microscopic matrix of spheres actually pulls apart and creates physical gaps in the universe?
Not gaps, no, but extreme geometric distortion. The wild phase features highly complex fractal structures known as Gasikovich, or Kakeya, needle sets.
Kakeya needle sets. Okay.
Yeah, and without getting bogged down in the pure math, you can think of a Kakeya set as a geometric structure designed to achieve the maximum possible directional complexity while taking up the absolute minimum amount of volume.
Wow, okay.
Imagine trying to rotate a needle a full 360 degrees inside the tiniest possible space. The maneuvers required create an incredibly chaotic, jagged mathematical structure.
I can picture that.
And because of this microscopic geometric chaos, the vacuum experiences wild subscale fluctuations. It generates what the paper calls arithmetic jitter.
Arithmetic jitter. That sounds like a computer glitch. Are you saying reality generates geometric rounding errors that could physically crash the structural code of the universe?
It would be catastrophic if the universe didn't have a specialized shock absorber built into its geometry.
A shock absorber for reality.
Exactly. To handle this arithmetic jitter, the vacuum utilizes a very specific shape called a gyrobifastigium.
The gyrobifastigium. I feel like I'm casting a spell just saying that.
I know, it's a mouthful. But it is a real geometric term for a self-tessellating Johnson solid. You can visualize it roughly like a complex triangular tent.
Okay, a tent.
The shape acts as mechanical mediator. When the microscopic wild phase generates chaotic jitter, the gyrobifastigium literally adjusts its roof angle.
Wait, it moved.
It mechanically flexes. By changing its internal angles to absorb the geometric shock, it smooths out the rounding errors. This mechanical flexion allows the chaotic vacuum to safely cluster together into highly stable structures called 9-tile metatiles.
So the system preserves local stability by absorbing global chaos.
Precisely.
It's like earthquake retrofitting for the fabric of reality. The building sways so it doesn't snap.
That is a perfect way to look at it.
But, okay, even with a geometric shock absorber flexing to handle spatial errors, how does time function in all this? I mean, if the physical space is constantly jittering and mathematically correcting itself, shouldn't the timeline of reality get completely tangled up?
You'd think so. But that brings us to one of the most innovative concepts in the IFD framework, its temporal model.
Oh, okay, let's hear it.
To keep the timeline smooth, while the spatial geometry is constantly flexing, IFD employs a three-dimensional temporal framework.
Three-dimensional time.
Yes, time is not a simple single-lane highway moving from past to future. Space-time operates as a concurrent superposition of three distinct temporal states.
Okay, wait, I want to make sure I grasp this. Are you saying the past, present, and the entire future are all happening at once, just layered on top of each other?
Not quite the entire future, and that is a crucial distinction. The three states are first, the realized metric, which we experience as the present.
Okay, the now.
Right. Second, you have the future search space. That is the mathematical realm of possible upcoming geometries.
Like the options menu for reality.
Exactly. And third, you have the fixed arithmetic constraints of the past. It functions as a triple-proof architecture.
So, by superimposing the rules of the past and the possible geometric configurations of the future onto the present moment, the universe is essentially pre-calculating the next frame of reality.
That is a brilliant way to phrase it, yeah. This 3D time structure ensures that any arithmetic instability, that wild jitter, is absorbed by the future search space and resolved before it can ever manifest as a physical collapse in the present metric.
The code checks itself before it compiles.
Exactly.
Man, that is elegant. So, knowing that space is this fail-safe protected, densely packed fractal matrix of microscopic spheres, dynamically managing time and geometry, we have to talk about black holes.
The ultimate stress test.
Right. Normally, we think of a black hole like a cosmic sinkhole, a bottomless drain in the universe where a dying star collapses inward forever and the math of gravity just gives up. How does the IFD matrix handle an entire star collapsing onto it?
Well, it requires completely redefining what a black hole is. Under the IFD framework, black holes are not material objects or bottomless pits.
What are they then?
They are, in the paper's terms, dynamically sustained, coherence-admissible space-time configurations.
Okay, let me try to translate that into a visual. Let's say a massive star, which exists in our macro scale, the S sub n scale runs out of fuel and collapses.
Right.
It hits the event horizon. Instead of falling into a bottomless singularity, what is actually happening?
When that macro-scale matter hits the event horizon, it undergoes a profound structural phase transition against the S sub n-1 matrix.
A phase transition.
Yeah. The paper draws an analogy to the liquid vapor critical point of a Bose fluid. The collapsing matter isn't falling down a hole, it is transitioning across a dimensional threshold into the subscale matrix.
Okay, imagine throwing a massive block of ice into an ocean made of incredibly dense, vibrating microscopic marbles.
Oh, I like that.
The ice block doesn't just vanish into a void, it hits the marble ocean, and the sheer density of those S sub n-1 spheres begins to break the ice block down, changing its state.
Exactly.
But this brings us back to the information paradox. If quantum mechanics demands that the blueprint of that ice block the star is never lost, how does a dense ocean of marbles preserve that information while grinding it up?
This is where IFD reinterpretations Hawking radiation.
Okay.
Standard physics assumed Hawking radiation was the black hole slowly evaporating away and, deleting the star's information in the process. IFD argues that Hawking radiation is actually coherence leakage.
Coherence leakage. So the star's energy leaking out as it grinds against the subscale matrix?
Yes. As the macrostructure of the collapsing star encounters the immense density of the subscale matrix, mechanical displacement occurs. It bleeds kinetic energy.
But the information?
The quantum information of that matter is not destroyed. Instead, it is dynamically re-encoded.
Re-encoded into what?
The macro information gets translated into highly complex oscillatory patterns within the S sub n-1 spheres themselves. The paper refers to these as murmuration patterns.
Murmuration patterns, like a flock of birds.
Exactly. The information of the star ripples through the fractal matrix, perfectly preserved as geometric oscillations.
The matter of a dead star murmuring through the deep fabric of the universe, that is a hauntingly beautiful concept.
It really is.
But we need to look at the sheer physics of this phase transition. If an entire star's worth of mass is compressing against this microscopic ocean, there has to be an immense amount of friction.
Oh, massive amounts.
So what physical mechanism stops that collapsing mass from just overpowering the matrix, crushing the marbles, and forming that infinite singularity anyway?
The mechanism stopping it is mathematically defined as geometric friction, and it's represented by the Greek letter phi.
So the vacuum isn't just a passive wall. It actively pushes back against the star.
Yes, it acts as a topological drag. The vacuum physically resists the forced mutation of its internal geometry.
Right.
And the paper maps this resistance to a mathematical concept called Schramm-Lohner evolution, or SLE, diffusivity.
SLE diffusivity. I always picture Schramm-Lohner evolution like trying to compress a sponge that is already completely saturated with water inside a hydraulic press.
Okay, let's play that out.
As the dying star the press tries to crush the vacuum physically stiffens. The water has nowhere to go, so the structural resistance of the sponge pushes back with incredible force.
That is a really solid way to visualize it. As matter tries to compress the vacuum lifts its dissipative charge to unity.
It pushes back mathematically.
Right, and this incorporates a scaling factor denoted as a substar, which guarantees that the density of the collapsing matter eventually stabilizes at a hyperdense plateau.
A plateau. It stops. The collapse halts before it reaches infinity.
Exactly, it hits a rigid sphere packing limit. The subscale spheres of the matrix simply cannot be compressed any tighter without violating their fundamental geometry.
So the physical density reaches a finite, calculable maximum.
Yes, and by doing this, the mathematical necessity for an infinite singularity is completely eliminated.
Wow. So once the star's matter crosses that event horizon threshold and hits this rigid sphere packing limit, how does it actually behave inside the black hole?
It behaves as a stiff relativistic fluid. The structural back pressure of the subscale matrix, which is trying to maintain its shape against all that crushed matter, is modeled by a polytropic equation of state.
Referred to as P sub n minus 1.
Right. When physicists run the numerical solutions for this kind of extreme fluid using the Tolman-Oppenheimer-Volkoff equation, the results are astonishing.
What happens?
The speed of sound within this dense fluid interior asymptotically approaches the speed of light, but it never ever exceeds it.
Wait, meaning that even when you look up at the night sky and realize the stars and galaxies are actually hurtling away from us at accelerating speeds, you are looking at the effects of dark energy.
Right.
It is an invisible force stretching the universe apart, and for decades, cosmologists have viewed it as some exotic, undiscovered particle or a spooky new field.
But IFD argues it isn't a new particle at all. Dark energy is simply the macroscopic manifestation of that exact same S sub n minus 1 matrix back pressure trying to reach thermodynamic equilibrium.
Hey, the very same geometric friction that pushes back against a collapsing star is what is pushing the galaxies apart.
Yes. Consider the vast voids of the cosmic web. The unimaginably huge expanses of empty space between galaxy clusters where macroscopic matter has essentially been cleared out.
The truly empty spaces.
Right. In those dark voids, the S sub n minus 1 fluid exerts its pressure unimpeded by heavy matter. The outward topological drag in the vacuum trying to stretch into its optimal geometric state translates directly into the dark energy pressure we observe from our telescopes. The IFD equations literally map the observed dark energy pressure as approximately equal to the negative pressure of the S sub n minus 1 equation of state.
It grounds an abstract cosmological mystery in pure structural fluid mechanics. It is simply the vacuum of space trying to stretch its legs in the empty voids.
It is deeply elegant. However, for a universe running on this kind of complex, eternally descending fractal hierarchy, there is one final ultimate failsafe required to make the entire global system stable.
Another failsafe.
Yes, because without it, the universe risks falling into infinite symmetries or suffering an informational heat death. It needs a topological cutoff.
A cutoff.
Ramona.
A way to cap the system so the math doesn't spiral away into an infinite loop. What shape does the universe use to cap itself?
It uses the Einstein monotile, colloquially known as the hat tile.
A hat, a cosmic hat.
I know, it sounds funny, but it is a specific 13-sided aperiodic shape. The term aperiodic means it can tile an infinite two-dimensional surface forever without ever perfectly repeating its pattern.
Never repeating, okay.
In the IFD framework, this 13-sided tile acts as a geodesic trap. As the structural code of the universe constantly processes data and geometry, specifically through something called the SOMOS 8 sequence, it generates mathematical remainders.
Arithmetic failure remainders.
Exactly.
It's the universe's leftover change from all those microscopic geometric calculations.
That is a great analogy. Now, if those remainders were allowed to accumulate, they would eventually stack up and form infinite singularities across space.
It would break the system.
But the 13-sided hat tile physically prevents them from accumulating. Because the tile's pattern never repeats, the errors can't stack cleanly.
Ah, I see.
The aperiodic trap catches these mathematical remainders and forces them to spread out into oscillatory murmuration patterns. And here is the kicker. Those spread out captured mathematical remainders actually define the mass spectrum of our entire universe.
Wait, really? The 13-sided hat shape acts like a cosmic garbage collector for mathematical rounding errors, and instead of letting those errors crash the system, it recycles them into the very foundation of mass.
Yes.
It turns errors into physical reality.
It completely resolves a mathematical paradox by making it the cornerstone of physical existence.
We have covered massive ground today, so let's synthesize this journey for you listening.
Good idea.
The infinite fractal descent framework offers a rigorously mechanical way to unify the broken laws of physics. By viewing the vacuum of empty space not as a smooth, passive void, but as a densely packed, nested fractal matrix of microscopic spheres, IFD fixes the glitches.
It really ties it all together.
It eliminates infinite singularities inside black holes by hitting a rigid sphere packing limit. It saves quantum information from being destroyed by re-encoding it into murmuration patterns. And it explains dark energy, the great mystery of the cosmos, as mere thermodynamic fluid mechanics, just the structural back pressure of the vacuum stretching out in the voids.
But, this leaves us with a provocative new implication to consider, a final thought to chew on.
Oh, I'm ready.
The IFD framework relies on infinite fractal descent. The microscopic matrix S sub n minus 1 stabilizes our macroscopic universe, S sub n. But fractal descent implies it doesn't stop there.
Are you suggesting we look up instead of down?
Exactly that. If our universe is stabilized by the microscopic jitter beneath us, what if our entire macroscopic universe, all our galaxies, our black holes, our massive dark energy expansion, is actually just a tiny microscopic S sub n minus 1 arithmetic jitter for an unimaginably larger, infinitely vast universe looking down at us?
Wow.
Are we just a subscale failsafe keeping a higher reality from collapsing?
So the next time you stare at a blank, smooth canvas or look up into the endless dark voids of the night sky, just remember, there is no such thing as empty space. You just haven't zoomed in or zoomed out far enough yet. Thank you for joining us on this deep dive. Keep questioning the universe around you.